So welcome to this webinar. This week we have the Copenhagen Marathon, and in the marathon of webinars for the VELUX Project Development Guide, we are just past the halfway mark. This is webinar number 4 out of 6, and today we're talking about life cycle assessment combined with BIM. So I'm here together with Alberte Groslev-Bunde, who's my colleague here at GRAPHISOFT Center Denmark. My name is Thomas Grabæk. I'm the host for the webinar, and Alberte will be changing places with Shivani Mutatkar and Elham Beek from VELUX, who will present all things around LCA calculation. So we'll slowly start, and then we'll have an action-packed webinar with a lot of information. So let me just share my screen. So, webinar number 4, life cycle assessment in a BIM workflow. In a BIM workflow is one of the important things here, because often LCA calculations are separated from the drawing material, and what we want to show is the importance of bringing those two things together. And in the first webinar, where we talked about the sketching phase, the early phases of the project, we also touched down a little bit on LCA, because it's important that you calculate also in the beginning of your project. But today we're going to go much more into detail with the more finalized LCA calculations. The agenda of the day, first is an introduction to LCA in general, a little bit about how the rules are for complying with building codes, mainly across the EU. Then we have something about environmental project declarations, which is the EPDs in short, and they tell how big the climate impact from products are. Then we move to energy calculation, because the climate impact from emissions from energy sources, that is also a big part of LCA and must be taken into account with all this. And then we bring everything together in the BIM model and carry on with a full LCA calculation directly in the BIM project. And then in the end, we're going to check out some roof windows and see how different product configurations of windows, they will impact the LCA. And that will take around 1 hour, and hopefully this time we have room for some questions before we wrap up and leave it for the next 2 webinars. So let's jump directly to this project. All these webinars are part of the Project Development Guide, which is a project within VELUX that we are helping to perform. You can go to the website, the landing page at velux.com/project-development-guide. And here you'll see the already finished webinars as videos. They're also on YouTube. And you can also see the project material, so you can flip through the drawing materials of the project. You can download the ArchiCAD file, the IFC files, some DVGs. And you can also go into the full project in the BIM viewer called BIMX and jump between drawings and 3D models. So please go to the landing page and explore all the materials there. The project development guide are based on a real life project in Lystrup, just outside Aarhus in Denmark. It's called Home for Life. It's a VELUX building from 2009. And back then it was already a landmark of sustainability within small housing. And we just let us inspire from this project and used it for producing the drawing material, do the sketching, detailing phase, the LCA and everything. But we have updated the building. So we have made small changes, especially in materials, to make sure that we can comply with the newer, stricter rules of the updated building codes in Denmark. This building was done by architects in collaboration with Espensen Consulting Engineers. and it's a really nice building. To learn more about life cycle assessment, or LCA, I'll have Alberta explain everything.
Yes. So I will get into what an LCA is and what an EPD is, but before I do that, I want to take you through some context of why LCA is so important and so relevant right now. So what we're looking at here is how much the construction industry emits on a global scale and also on a Danish scale. So the construction industry...
the whole footprint of the ACO industry.
Yeah, it takes up 40% of the global emissions compared, where the remaining 60% is the rest of all other industries. And in Denmark, the construction industry takes up 30% of the global greenhouse gas emissions. So that is a really large share. It also means that if we change how we build and how we design, it will make a big change for the overall emissions. And if we break down the Danish numbers, we can see that 1/3 of the emissions from the construction industry comes from the materials, and 2/3 comes from operations. So this means that we really need to focus on both of these things to make an impact or lower the emissions. And if these numbers isn't convincing you of how important looking at LCA or LCA in the building industry is, then it might convince you that it is not optional. So at least not if you are from an EU country, because LCA is already a part of EU regulations or the future plans in the EU regulations. As we can see here on the small timeline, by 2027, each country have to publish a national roadmap for introducing limit values for building LCAs. And by 2028, countries it's mandatory to make an LCA calculation for all new buildings over 1,000 square meters. And by 2030, it's mandatory for all new buildings, including threshold values.
And I think that the threshold values are the important thing, that there's a limit. It's not enough just to calculate the LCA. You have to be within some kind of limit. And that will differ a little bit from country to country, how you define the limit and what it is. But in a Danish context, we've seen that really changes how, especially architects, look at sustainability when they have to make a building that performs under a threshold, a limit of CO2.
Yeah. And also, as we can see on the map, there are some countries that already have values, limit values in place nationally. For example, Denmark and France and the Netherlands. And then all other countries are planning on introducing limit values. So what is an LCA? LCA stands for Life Cycle Assessment, and it is this standardized method of estimating environmental impact of a product system, in this case for a building, throughout its whole life cycle. And I will in 2 slides go into what this life cycle takes into account, but essentially it's from extraction of raw materials until end of life, so from cradle to grave. And the method LCA can assess many different environmental impacts. For example, global warming potential or land use or water consumption. But according to the future EU regulations and also according to the Danish regulations, we only have to look at global warming potential, or it's the only mandatory environmental impact we have to look at, which represents greenhouse gas emissions. And from a Danish context, so I will be talking about LCA in general, of course, but I will also talk about it from a little bit of a Danish perspective. And in Denmark, all new buildings must report an LCA calculation, and almost all buildings need to stay below a certain LCA threshold value. As I just said, it's only mandatory to include the global warming potential, and this LCA result therefore has to be in kilograms CO2 per square meter per year, where this per year is the global warming potential divided by 50 years, because in Denmark that's what we have decided the lifespan of a building is.
Then I just want to add that this CO2 is called CO2 equivalence. So that's why we try to remember always to write EQ after the CO2. And a CO2 equivalent is because there's a lot of greenhouse gases that affect the climate. And it would be really difficult if we had different thresholds, different limits for each of these climate gases. So therefore we calculate different gases as CO2 equivalents. So one of the gases that cows burp out is called NO2, and that pollutes 28 times as much as CO2. So therefore, the CO2 equivalent of that gas will be 28 times, and then you have one number for all greenhouse gases that are comparable. So that's the secret behind the EQ in CO2 equivalence.
Yeah. So that's how to understand that unit. Then talking again about the life cycle of the building, according to the ISO standards, it's divided up into different life cycle stages and modules, like you can see here. And the ones marked with orange are the ones that are mandatory in Denmark. So that is the product stage, it's extraction of raw materials, transportation of raw materials to factory, and manufacturing of building materials. Then there is the emissions from the construction side and the transportation to construction site. We also have to include parts of the use phase, so replacement of materials, and then also a really important one is the operational energy. And then we need to include waste processing and disposal, and module D, which represents the future benefits of recycling. But this module D is outside of the threshold calculation. So to sum that up, and a building LCA needs to include emissions from the materials, what we call the embodied emissions. It needs to include the energy or the operational emissions, which comes from the energy calculation, and also the emissions from the construction side, and that is calculated separately. So everything except for the emissions from operation and from construction side is tied to the materials used in the building. And to understand those material-related emissions better, we use EPDs, or environmental product declarations. And what these are, it's third-party verified documents that are essentially life cycle assessments of materials or of products instead of buildings. So in these documents, we also find results from different environmental impacts, for example, global warming potential from the production stage, from the end of life, and from recycling potential. And the result comes out in per unit. So there is this declared unit for every EPD. For example, if you have an EPD of insulation, you would maybe have a declared unit of cubic meter, and then the result would come out in kilograms CO2 per cubic meter. And that's what we use in the LCA. Then most EPDs also have a lifespan for the product, which is important for when you have to replace the materials during the lifespan of the building.
So lifespan can both be materials and building components. So it could be a window or a door, but it could also be a material that goes a roofing material or a facade material.
Yeah, exactly. And these EPDs are not required for a manufacturer to make, but there is a high demand for it. So you would often see that if you find a product, they also have an EPD. But in the case that the material you're using does not have an EPD, you can use national average data. At least in Denmark, the Danish Building Code have provided a big list of materials with average CO2 data that we can use.
And when we talk about this EPD use, if we had product-specific EPDs or generic EPDs, that's how it's looked by the EU for their rules and for the Danish building codes. But if you look to DGBN sustainability certification, then there's a benefit of using product-specific EPDs compared to generic because you have a small penalty for using the generic data.
Yeah, exactly. But of course, in different design stages, maybe in the early stages it's easier to use generic data, and then later on you can begin to look at more product-specific data and therefore also get a more accurate LCA result.
True.
Yeah. So yes, what we did in our project is that in the early design stage we made this material diagram where we mapped out the materials we thought were potentially very good sustainably or in a sustainable context, but also appearance and the thermal properties we wanted.
People might remember that from the first webinar.
Yes, exactly. And this gives us a good starting point in our project, but it's also based on assumptions and kind of a rough way to look at it. So that's why as we moved on in the project, we started working more actively with LCA, which allows us to test different materials with real CO2 data if we use product-specific EPDs. So instead of relying on this intuition, we make informed decisions.
So then that way, the process of the LCA, it follows a process of the architect's design. So in the early phases, we don't know too much, but we assume. And then slowly throughout the project, we get more and more specific. We calculate, we test, we try out different solutions, and then we find the one that we know is a better solution.
Yeah. And then to something a little bit different. As I have been mentioning a couple of times now, it's not only required to make an LCA, we also have to stay under some different threshold values, and that goes for other countries but also for Denmark. And in Denmark, this threshold value was introduced in 2023 as a threshold value of 12 kilograms CO2 equivalent per square meter per year for all buildings above 1,000 square meters. And then in 2025, a new revised threshold was introduced, an average threshold of 7.1 kilograms CO2, and then in 2027 and 2029 the threshold will be revised. And we can't really use this average threshold too much except for realizing that the threshold or the requirements get stricter and stricter because there is a specific threshold for every building typology. So for example, if you want to build a holiday home under 150 square meters, you need to stay below a threshold value of 4 kilograms CO2 per square meter per year. If you want to build a single family house or a tiny house or maybe a holiday of at least 150 square meters, you need to stay below a threshold of 6.7. And then there are different ones for apartment buildings, office buildings, institutional buildings, and other buildings. And these get stricter with time. And then here in the end, there is also a separate threshold value for the construction process, which is outside of the LCA calculation you make of the building itself.
So you can see it like the black values are the CO2 thresholds that the architects have to be below, and the orange one is the one that's documented by the contractor. So the contractor must make sure that the transportation from factory to building site and the energy used on the building site, along with waste, is less than, for now, 1.5 kilograms of CO2 per square meter building.
Yeah, exactly. And then before Shivani or Elham takes over, I just wanted to look at this slide where we can see the threshold values and how they change for Denmark and for Netherlands and for France. And it's hard to compare the values between countries because there might be different requirements for how to make an LCA. But what we can see is there are different approaches to how a limit value can look. So in France, they have a separate limit value for the energy use, and in the Netherlands, they have a completely different unit set for their limit values called environmental cost. So there are different approaches to this, but what is common between these countries is that the limit value will decrease with time. And then I think it is time for Elham to come over.
Yes, so we'll just be changing faces here. So what has already been demonstrated by Albert is that the LCA calculation is made from two things. There's the CO2 from the building materials of the project, and there's the CO2 from the energy emissions for the project. So there's materials and there's energy. The energy is for cooling, heating, ventilation, and lighting. And we always have to bring these two things together. So we'll be looking at the energy calculation later on, but right now we're going to look a little bit more in detail on the building material CO2 footprint. And to calculate that, you use environmental product declarations, or EPDs. And Elham, you're going to talk a little bit about how they're built.
Yeah, so in this section, I would like to talk about VELUX EPDs and how they can help designer understand and also compare the environmental performance of different product solutions. Yeah, and in this section, we deep dive into VELUX EPDs. So, but before diving into specific EPDs, it's important to first understand the role of program operators, or called POs. So program operators are the organization responsible for managing, verifying, and publishing EPDs in different countries and regions. And EPDs are developed according to internationally recognized standards that they make sure that the data is transparent, valid, and also comparable. And as you can see in the slide, there are many program operators across Europe. And they work together through a platform called Eco Platform Association. And this association is there to harmonize the methodologies and calculation rules and verification procedure that all these EPDs are following. And this alignment is important because it increases the consistency and the trust in data in this environmental declaration documentation.
And the reason that we have this, these POs are that we need a third party to evaluate and certificate.
Exactly.
So we're sure that it's not some product manufacturer that just signs off by himself.
Yeah, so that's why they are there. So the EPDs are valid and also harmonized, because if you want to use EPDs in different markets, there should be something behind that. You are trusted in the data, and also you are sure about consistency of the methodology they have used to calculate the EPDs.
Definitely.
Yeah, and just to say that in VELUX, our EPDs are on the platform called IBU in Germany, which is one of the most recognized program operators in Europe. Yeah, and then we can go to the next slide, that we can talk about what VELUX EPDs cover, basically. So VELUX offers EPDs for a very broad range of products today, and we cover currently over 96% of residential products, including windows, flashing, and installation products portfolio. This is important because it gives our customer, architect or consultants, access to verified EPDs. That, as I said, it's a very broad range of product. And to just give some examples, we have traditional PU and also wood roof windows. We have flat roof windows, sun tunnels, window operators. And it's very important to say that our EPD is also covering the installation products, because environmental impact is not only valid linked to like window itself, it is also about the full integration of the solutions around it. And on the right side, you can also see how comprehensive is an EPD scope. It's like many layers in a window, as I just named some of them. And you need to really consider all these, and then all these come to a product, a component that is a window. Yeah, and this is about comparing VELUX EPDs and say, okay, it really differs from product to product. So if we just look at the wooden window and then it's 2-layer, and the operation of window is from, let's say, in the middle, and when we go to the top hung, which is from the above. So operation actually can add to the complexity of the product and add to the CO2 of the product. And then when we go from a 2-layer to 3-layer, of course, we're adding another layer to the material, and this also adds to the carbon footprint of the product.
So that's the layers of glass.
Yes, when we go from 2-layer to 3-layer, we're actually adding 1 layer to the glass, and of course, we're adding to the embodied carbon and is material add-on. So of course, it increases the carbon impact of the product.
And this is exactly why it's really important to remember that the LCA consists of the building material CO2 and the energy for use CO2. So when we add a 3rd layer of glass, the building material CO2 will rise, but the energy CO2 will be lower.
Exactly.
Yeah.
So we need to really have this holistic understanding of the product. Of course, it brings value in terms of building performance, energy saving, but you have to compromise on one side, but there is a trade-off. So you need to take into account that. But that's why it's important to understand the differences between the product and how does it impact the environmental impact of the product. And another example is if you have wooden frame and then you have PU frame, it could really impact in terms of the material choices. And apart from the window, we also have accessories, right? We could have roller shutter, blinds, and they are also add-ons to the product. So we don't, of course, see just window as it is. We always see it as a package that if you want to save energy, let's say in summer, you put a roller shutter on top of your window, there is an add-on to the embodied carbon of the product. But this is all important for the designer because it's really influenced the decision-making in the process. Should I put a roller shutter on top of my window? If I do, then how is the embodied carbon? How much I'm saving in the energy? So it's like a decision-making tool.
We'll make that a cliffhanger. So in the end of the webinar, you'll actually see what the difference is of adding the roller shutter or leaving it out.
Exactly. Just to say that EPDs are not only documentation tools, they are decision-making tools that actually helps to understand the environmental consequences of the different design choices and also may support more informed decision-making process. And I will go to last slide from my part. I just want to show some example of VELUX EPDs that they are considered actually low CO2 products, and I just want to explain why they are considered lower carbon impact solutions compared to similar products in the markets. So if you look at the left side, there is a wooden roof window, which is actually 3-layer, and the carbon footprint is 105 kg to CO2 equivalents per square meter over the lifespan. And even though it is a triple glazing, and of course increase the embodied carbon, but it has a wooden frame that helps to reduce the overall impact. And when we look at the other comparison in the market with the same triple glazing, we can see that solution is actually lower CO2. It has lower CO2. And then if we look at the right side, this is a new product we have launched this year. It's called NEP roller shutter, and it is 40% less in carbon as compared to the previous generation. And it is also lighter, so this actually helping to bring down the the environmental impact. And yeah, as you can see, it's 110 in the lifespan of 30 years.
So in the future, we don't only have to look at the aesthetics of the product and the price of the product or the build quality, but also the CO2 footprint, because it really differs on the LCA calculation, what kind of products you use. And if you want to be below a threshold, you have to choose products that has a low CO2.
Yeah, but I think it's also what all you said is important, but also the products that actually help us to have a good indoor climate and building performance. So we talk about the shutter. Yeah, it should be low carbon, it should be aesthetically appealing, but it should also, the function of it is also it's heat protection, right? So it provides a good indoor climate in a summer that maybe you don't need to really use ACs in some countries. So it's also important to be contributing to a good indoor climate and building performance, good building performance.
And we're going to see later that it actually, usually in some countries, that even though we're far north in Denmark, we still need to have some kind of heat protection from the sun.
Exactly. But yeah, I will give it to the girls to continue.
Yes, so we'll be switching back to Alberta because to calculate this the LCA, we need to understand how the energy calculation affects the CO2, and it does so by emissions. So when we produce energy, there's always some kind of emission, even from renewable energy as sun and wind. So we have to kind of multiply the energy consumption by some kind of emission factor. And that's a little bit more complex than you might think. So I think if Alberta is ready, we're going to jump right into it.
Yes, and I should have listened to what you just said because I might repeat.
I just said that.
Yeah, okay, super. So we need to include this operational energy in our LCA calculation, and normally from an energy calculation we get the result in kilowatt hour, and we use this thing called emission factors to convert the operational energy from kilowatt hours to kilogram CO2. And what we're looking at here is a graph of the Danish emission factors and how they're going to change from 2025 till 2050. And this is Denmark, but this is also what you would see in most other countries because the emission factors decrease as the energy grid becomes greener.
The energy mix will be greener and greener for every year.
Exactly. And yeah, at some point in 2030, it will stop getting greener.
So when we see a graph like this, it's probably more political than it's factual. So in Denmark, we have a law that will try to limit the emissions for the whole country by 70%. So there's a lot of initiatives going on right now that will aim for a really low CO2 footprint for the whole country in 2030. So that's why the graph is going steep downwards until then, and then it flattens. And I guess that we will keep seeing lower and lower emission factors, greener and greener energy mix, also in the years after 2030 and after 2050.
Yeah, I think you're right. Yeah, so we see it here for electricity, for district heating, and for natural gas.
And on the left side of the slide, there's just a picture from the Danish building codes, because there's a small file that determines how we should set the emission factors for electricity, district heating, and gas for the next 50 years.
Exactly, yeah. And I really want to show you how to convert this energy from kilowatt hour to kilogram CO2 in practice. So what we're looking at here is a table that's a part of the Danish ArchiCAD template, but it's also a part of the model that you have access to. And it is a table of what emission factors to use depending on the year of commissioning and also your energy system, so district heating, electricity, or natural gas. And it is these numbers that I will use.
And I think it's really important to understand the value of this, because in Denmark we say that with ArchiCAD and Design LCA, you can do the whole LCA calculation without jumping out of your BIM tool. And therefore we have added all the needed values inside the template, so you can just look them up and do everything within your BIM application.
Yeah.
So that's why we have these special numbers.
Exactly. And it's of course the Danish emission factors you're looking at here. So it's if you are doing a building in Denmark. But what you do is you have the energy calculation results. And here we have heating. It's 14.6 kilowatt hour per square meter per year. And since the heating is a heat pump, it's also based in electricity or in El.
And we've been looking a little bit on this in earlier webinars, because VELUX has made these calculations with an application called IDA-ICE. So they've been refined through the beginning of the project to look at how sun, wind, and rain will change the performance of the building. So that's a result, 14.6 and 2.8 from IDA-ICE.
Exactly, yeah. And the other 2.8 is from ventilation and lighting. And then our year of commissioning is 2026, and that's why because everything is based in electricity, we only have to use one emission factor for electricity, which is the one you see here, 0.0287 kilograms CO2 per kilowatt hour. And what you do is you sum up the electricity use and multiply it with the emission factor, and then you actually get the result of how much CO2 equivalent your operational energy emits per square meter per year. But when we put it into Design LCA, we need to have the unit in kilograms CO2 per year, or the annual.
Whole building.
Yeah, exactly. So the annual CO2 emissions. So that's why we here multiply the result with the heated area, 200 square meters, and put it into this Design LCA settings tabs, which we will show you where is.
Exactly.
Yeah. So I think actually we will jump right into the live demo so you can see how it works.
Yes, so here we have the ArchiCAD project, here we have the building, it's live, and I already brought up the main palette of Design LCA. And Design LCA is a free LCA calculator. You can find it for download on the internet if you search for Design LCA. And that brings LCA calculation inside ArchiCAD. You can do both the calculation for CO2 on materials and for the energy use, but we didn't use the energy part inside ArchiCAD, but we did that in IDA-ICE for this project, but it really doesn't change much. So what you see here is the whole calculation. If you take it line by line, the first line is the operational energy, and it's the total global warming impact is mentioned in the first column. And then it's divided by the area of the building, and then it's divided by the 50 years. So in the last column here, we have the result as it should be reported in the Danish building codes as as kilograms of CO2 per square meter per year. So first line is energy use. The second one is building components. So all the materials is actually listed in one line, except for doors and windows, because they have a lifespan. So for the doors and windows, for doors it's 25 years, and we calculate for 50 years. So we actually have to multiply by 2 to have the full impact for the whole timeline of the LCA. Windows are also here separately. And the last part is the material used for installations. And by the Danish building codes, we can just enter that as a value per square meter. So that's actually not calculated from the BIM model. Everything else here is automatically calculated from the model. So everything you model is automatically included in the LCA. We don't have to write numbers down. We don't have to copy paste numbers or anything else. It's directly from the BIM project. Then we have some settings, as Alberta said, and those settings are the considered service life. So how long time are we calculating for? It's 50 years. It can actually automatically enter the square meters of the buildings if we're using the energy calculation within ArchiCAD. We have chosen to do it manually here and enter it. So these are the square meters used to divide the CO2 from the energy use. Then the CO2 from energy use can also be automated within ArchiCAD, but here we have the result from IDA-ICE, which Alberta just showed how we multiplied with the emission factors, and then entered manually. Then in Denmark, we have a reference floor area, and that is the floor area we use to divide the material CO2 from, so that's here. And in IDA-ICE, we already included the energy from solar panels, but if we didn't, we can just add a value, for example, 25 kilowatt hours per square meter per year. So we don't have to model the solar panels to get this included in the LCA. Then we can see which modules of the LCA is included in Denmark. In other countries, we might have to remove some tick marks or add some. And then in the bottom here, we have some comparison to other values. So we have entered in the Danish version, the vacation homes, they have to be less than 4. Single family houses have to be less than 6.7. So that's our threshold for this project, 6.7 kilograms of CO2 per square meter per year. Then we have apartment buildings on 7.5 and other building types like hospitals for 8. So this is why we see our project is placed correctly within the other project types or typologies. Then we have a small diagram showing where most of the CO2 is from. The orange part is from materials. The blue one is from energy use. Green one is installation. Yellow is window, and gray is doors. But that's not enough for me to really understand how I can limit the CO2 on this project. So I actually want to make a report. Let's do that. An element CO2 report. And the element CO2 report will just take a second to load. So that's kind of the fun thing of doing this live on a real project. So now designers, they will recalculate the whole project and show me all objects, not materials, but objects that are in the model. First, it's divided down by the layer it's modeled on, structural walls, partitioning walls, roof construction, and so on. Then I can see with a dark gray bar here, the whole summed up CO2 footprint for this layer. And then I can see all the different objects, which is mainly windows and doors and the structural members on this layer. So on structural walls, it's mainly structural members. For roof construction, I can see the roof windows. So if I wanted to change one layer, it would be on the structural walls, and then I have to figure out what to limit from it. Since some of this is tied to the windows, I just want to show that on the VELUX objects, I can go to the settings, and here I can change the parameters of the window, but I can also find the EPDs. So there's a special pane here for links to EPD. So I can go to the window EPD. It will bring me to the internet, and I can download the EPD for this special window. I'll just go back to the model because I also want to show that we have entered the values from the EPD directly down to the object. So let me see if I can find that. I think I skipped it.
Yeah, it's right.
It's right up here. Yes. So because it differs from country to country which modules of the LCA you need to include, it's difficult just to automate this. So you have to go to the EPD, you have to find out the values, add them for yourself, and then write them down on this small field of the object, and then it will be taken into account for the complete LCA calculation. So that was the objects like windows and structural members. So there's also the material CO2 report. So let's just load that. It will take all materials that are used in the model. It will calculate some of them from cubic meters, some of them for square meters, and some by kilogram, and again show them here. It's divided by the layers materials are modeled on, and then in each material. So when I scroll down here, there's a lot of materials. So this is the whole secret about design LCA being an LCA-based design tool. So when I need to design with a lower carbon footprint, I'll find the layer that has the biggest CO2 impact. It was the foundation layer. And I can see within the foundation, my biggest problem is the concrete. So I might want to change that if I want to go for an even lower CO2 footprint. It could be steel screw for foundations or point foundations or some other kind of foundation for the project. That's the whole calculation, and you can see the end result here on our project is 5.12 kilograms of CO2 per square meter per year. But since this has to be documented for the municipality, for them to give us a use permit, I'll just want to show that part of the Danish template is these documentation layouts. And I can just zoom in a little bit. So here I have the whole calculation, 5.12. Then I have my area calculation for the areas of the building. I have the LCA per window and also for the VELUX skylights. And then I have for my doors here. If I jump to the next layout, it's actually material calculation, the one you just saw. So each layer of my building with each material and then the CO2 values for that. The last part of the documentation, it have to update. So it's recalculating all the time. So this one will give me my EPD data. So for every material, let me just zoom in a little bit more. I can see the whole list of different materials used on this project. And Design LCA will automatically figure out which materials from the template that have been used. And then it would show me the link to the EPD. And even though it's generic EPDs, it will still have a link. So when the municipality goes through my documentation, they can see how much I used of each material, and they can see the carbon footprint of the material is linked to an EPD. So that's my whole documentation. I just want to show this also. Albert already showed it. It's the emission factors of the project. So all the extra information you need to carry on an LCA is here, so you don't have to jump out. You don't have to jump out to the internet or a web platform or another calculation tool. Everything is contained within the template and within the project. Mm. Did I miss anything?
Yeah, I was thinking maybe we should show how we put EPD values on the materials.
That's a super good idea. So I'll just jump back to my 3D model. So I'll go to my Design LCA and my building material LCA settings. So that's the list I wanted to show. So here I have all materials inside my project. Most of them come from the template, of course, but we also added some for this project specifically. If I have materials that are called DK-LCA, they're from the template and with CO2 values from the Danish building codes. And the ones we have called EPD, like this hardwood cladding, then it's some new material that we made for this project and added the values from the EPD manually. Mm. And when I select a material here, I can see the CO2 values on the right side of this window. And I can see that the modules that are included in my project is module A1 to A3, C3 and C4. The other ones are grayed out because they are not relevant in a Danish CO2 environment. And I can just enter these manually. They're entered, or they're showed in two different ways, as a normal number for human beings, and then in this exponential scientific way of having numbers, it's minus 8 point something plus 0.2. And this is the way that the values are normally written down in the EPD. So it's easier to copy paste directly onto this one. So we can see both of them. Another important thing is the unit for measuring. So when you look in the EPD, you can see the calculation unit. Here it's cubic meters. It could also be square meters or kilograms of CO2. And if that's not put in correctly, then the values down here doesn't make sense. So it's important that you have both of these values from the EPD. And the last part is the service life, how many years these materials will last. And when it's more than 50, it will just use the numbers directly in the LCA calculation. But if it was between 25 and 50, you multiply by 2. And if it's less than 25, you multiply by even more than that. I think that's everything LCA, right?
Yes, exactly.
So I'll just jump back to the PowerPoint. I'm so glad I have my mouse back. Again, we're just changing places here because now Shivani will come on screen and tell us about how these LCA calculations can be used to determine if a special functionality or product will make sense when you try to balance the CO2 from materials and from the energy calculation. Yes.
Hello. Yes, so now to just kick things off, for our selected project in the VELUX development guide, let's look at the regulatory foundation of this project, which is basically the BR18 energy calculation, which is followed in Denmark. So when we're looking at the energy frame requirements under the BR18, we're actually looking at two different things. On the top, under paragraph 251, we calculate the building's total energy demand, which is basically the total energy required for heating, cooling, ventilation, hot water, and the lighting, which serves as the baseline for our climate impact. However, to meet the Danish regulatory requirements, we have to convert that demand to primary energy, which is outlined in paragraph 252. This is where we're actually applying the heating energy factors to account for efficiency of the source. So basically for electricity, the weighted factor is 1.9. For district heating, it's actually 0.85 in Denmark. So to document this for the building permit, we typically use the BE18 tool, which is the compliance standard in Denmark. But different tools such as IDA ICE or Climate Studio are also quite invaluable for more complex or dynamic modeling during the design process.
So this is kind of political thing that there's a penalty for using electricity in Denmark, and then there's a reward for using district heating, and that's actually added into the energy calculation.
Yes. So now that we've actually established the legal framework of BR18, let's look at how we calculate the energy frame and see how hybrid ventilation and passive measures allow us to actually reduce or manage the energy demand naturally throughout the seasons. So in this hybrid strategy, we are actually adapting the seasons to maximize efficiency. So during winter, we take advantage of the low angle of the sun as seen in the figure. And this is actually giving us the free passive heat. and we're still relying on the mechanical ventilation for hygienic requirements. But in the summer season, we shift to passive cooling and also using external shutters to prevent overheating. And this is allowing us to switch to natural ventilation by opening our roof windows to flush out the heat. So here we're actually balancing the mechanical and the natural ways throughout the seasons.
But what if it didn't? What if we removed the shutters?
Yeah, then I think that would be a case where we would see in the second graph in the slide where we're actually seeing the use of active cooling, and in that case we're actually increasing the total primary energy demand up to 46.4 originally from 41.4, as you can see.
So the case here is that with this intelligently made house, we have passive hybrid ventilation and passive shading. So in the summertime we can shield from the heat. But if somebody takes away those external shutters, then we'll actually have too much heat. So we have to have active cooling. That active cooling demands more energy. And that's what we can see here.
Exactly, because currently if we don't use any active cooling, which we would see in our next slide, we are still around 2% of the overheating hours of the occupied of the total occupancy. But if we don't use the shutters, then of course we would have to use some kind of a cooling, and that would increase the total energy demand.
And will actually increase the total energy demand with 10%.
Close to 9%.
Yes, so that's a lot. Sorry.
Yes. So now in this final slide, we can see how we've put everything together, and we're showing the impact of our cooling strategy on the building's total global warming potential. So on the right, we see a comparison with the active cooling. So we're at 5 kilowatt hours per square meter per year as the cooling energy demand. With AC and without AC, we're actually 0, but we have an overheating hours of about 2%. Using the adaptive comfort model, which we've already touched upon in our previous webinars. And yeah, when we're looking at the total life cycle assessment, the results are quite clear. By implementing these passive measures, we're actually reducing the building's total CO2 footprint by about 9%. So we're going from 5.6 if we use active cooling to about 5.12 if we go with the VELUX shutters and the passive measures as well.
So the CO2 footprint from the extra energy is much more than the CO2 footprint of the shutters. So from a sustainability point of view, it would make total sense to add the shutters to the windows and then save energy and save CO2.
Yeah. So basically, in summary, by actually integrating VELUX solutions as an active component in our design, we've demonstrated that passive cooling can actually eliminate mechanical cooling energy demand and cut the building's total CO2 footprint by about 9%. So this is actually proving that VELUX's products are providing many different benefits, which are ranging from providing a good indoor comfort, daylight, low CO2, and then basically by integrating them, we can still align with the ambitious LCA targets, which are quite low, and we're still aligning with the BR18 regulations in Denmark.
Yes, definitely. And in this small webinar marathon, we're getting close to the end and we have to sprint for the last part. So just to go through the key takeaways, LCA is a really good holistic way of looking at the total climate impact of a building. We need to understand EPDs. We need to have a good BIM model that will provide us all the information for the LCA so we can use it as a design tool. And then we have these special building parts, especially windows, that can work together with a hybrid ventilation and passive design strategy to optimize both the indoor climate but also the CO2 footprint.
Yeah.
So we managed to get through the whole information part of this webinar. all we need to add today is next Friday we are off. It's a national holiday in Denmark. So in 2 weeks from now, the next webinar is here, webinar number 5. It will be Friday, May 22nd, and it's about daylight visualizing and simulation, especially with the VELUX application called Daylight Visualizer. So please go to the VELUX LinkedIn page and find this webinar and sign up for it.
Yeah, and I think we've already answered a lot of the questions in the Q&A. So if there are any more that pop up, we will make sure that we've answered them in the LinkedIn chat. So
yes. So yeah, thank you to you, Shivani, and Elham and Alberta for answering questions along the way in the chat. Thank you to Lorena Jelinek for being behind the scenes and making everything work with the webinar. And I think I got a little bit smarter today about all this. And there's so many technical parts. So every time we touch on this, we understand more.
perfect.
Yeah. Thank you so much for staying on, and see you next time.
Yeah, see you. Bye.
Bye.